Thank you, Cliff, for that long, kind introduction, and I hope I'll be able to come up to your audience expectations. Thank you also to the two societies for the awards, for considering me worthy of the awards, and I'm really grateful to the committees for recognizing me, and I'm humbled, and it's really daunting to be giving two combined lectures in front of all the trained mineralogists. And one thing, as probably you can see from the title of my talk, I'm a soil scientist. I'm not a really true trained mineralogist. When I came to start my PhD in 1986 in Perth to work with Bob, we had a meeting, and he said, we have this large agricultural region in Western Australia, which is probably tens of thousands of square kilometers, and we want to know the mineralogy of these soils. And so you collect the samples, and let's see what we do next. So I spent first 6 months of my PhD traveling hundreds of kilometers and digging altogether 113 soil profiles all over Western Australia. And so I learned mineralogy by digging soil profiles, describing those profiles, and later on obviously examining the clay fraction of those profiles. So I come from a sort of a different pathway. I did not use the specimen minerals for my training. I used soil minerals. So, and I will share some of those results and later on some of the work which we have done. I'm not saying it's wrong to use specimen mineral. I have also used them, but I'm just letting you know the pathway that I have come from. And as I said, I'm a soil scientist. So what you will see today is more of a point of view of a soil scientist. During the last 20-25 years, I have collaborated with a lot of people, and the reason for those collaboration was really, I guess, I was very selfish. I wanted to learn lots of things from these people, and in here you will see people from all over the world. For example, I lectured at the University of Reading in the UK, and at that time there were not many mineralogists in England, so I came all the way up north to Jeff Wilson and the colleagues at Aberdeen, and I worked there. I came there a few times actually. We worked on some acid mine drainage samples in those years. So I just want to acknowledge all these people. There are a number of my students who have worked on aspects of minerals, which probably I will use some of their examples in my talk. Briefly to tell you what the talk is about, I'm going to very briefly, because there are a number of young people in the audience and they might not know who these two people, M.L. Jackson and George Brown, are. So I think it's important, and as a soil scientist or soil mineralogist, I think I have learned a hell of a lot from the work done by these two people. Then I'll give you some examples of using soil minerals and pure minerals, our fine oxides, particularly goethites and kaolinite and smectite, and show you what the implications of certain mineral imperfections are in terms of soil fertility, geochemistry of soils. And one thing I should point out, that coming from a soil science route, I have worked on applied aspect, as Cliff has already mentioned, and it's important in particularly, or it has become important in the last 15-20 years, that you can't really get any funding for any mineralogy project directly. So you have to use those mineralogical skills to solve some problems. And I think being trained as a mineralogist, it gives me so much of sort of power in terms of understanding lots of other things. And I will demonstrate that probably using some of the examples here. Okay, first let's have a look at some of the achievement of work done by Professor M.L. Jackson. As you can see, I have listed lots of things and almost everything what you would expect in mineralogy. He has done work on single crystal chemistry to sort of quantitative mineralogy, and then a lot of applications in geochemistry and soil fertility. But if I have to highlight a couple of things, these were the two probably the real highlights of Jackson's work, deriving the weathering sequence of clay minerals, which even we use today in our introductory, I guess, mineralogy lectures, teaching students what kind of mineral would you expect in different soil types based on that sequence, which obviously is based on how stable or weatherable various minerals are. And obviously the book on methods of soil analysis, which Jackson wrote. He actually produced two books, one on the soil chemical analysis and second the advanced method. Believe me that I think there would be very few people who have supervised 59 PhD students during their career. So it's just he was a really, really hard taskmaster, and I'm sure there are few people in the audience who have directly come through the family of Jacksons, either directly supervised by him or third generation trained through him. It's important to read this part here. One of the professors said that Jackson probably having the greatest total knowledge of soils in breadth and depth of any living soil scientist. So I think that shows the knowledge of the person and the sort of work what he started 20, 30 years ago, and we still are not able to follow up to the extent what he was able to. George Brown, once again, probably lots of European people already know about George Brown's achievement, and I'm sure almost everyone has used Brindley and Brown book in their career sometime. So once again, he started as a mineralogist straight after his bachelor's degree, and he was appointed when he was 20 years old. And I read somewhere that they had to I think, bypass some of the requirement, because you cannot appoint at that sort of a young age. So they bypassed and gave him a title which he was not entitled if you follow this strictly rule. He never finished, by the way, PhD, but he supervised some PhD students who are established mineralogists. So once again, it shows the sort of work what he did. Some of the highlights of his work. Most of his work probably appears in these two books instead of research papers. He did not write many research papers, but I think the distillation of most of his work, starting with the instrumentations, how to identify, prepare samples, appears in the book. But nevertheless, he did some important work on phyllosilicates and oxides. And towards the end, he was focusing more on the XRF analysis of biological samples. So anyway, I just wanted to acknowledge and highlight the achievement of these two great mineralogists. Okay, back to my talk, that how the imperfect mineral, or can the imperfect mineral control the fertility and geochemistry of soils. So when you look at the definition of imperfect, it could be damaged, or containing problem, or not having something. And when you look at this definition of imperfect in the context of the definition of minerals, a naturally occurring homogeneous solid with a definite but not fixed chemical composition in highly ordered atomic arrangement. In this context, all these imperfections could come in this homogeneous part, in chemical composition part, as well as in the ordered atomic arrangement part. So we are talking about the imperfections in all those three aspects of minerals. First of all, I will take some examples of iron oxides, remembering that iron oxides are important in soils because they exist almost in every soil type, iron being the fourth most abundant element after oxygen, silicon and aluminium. So it's present almost in every soil type. And if you think that silicon, quite a large proportion of silica is present in quartz, so it's not contributing a great deal in terms of the fertility or chemistry of the soil. Iron, in addition to aluminium, probably is one of the most important driver in this aspect. And iron being a redox element is probably more important, a lot more important than aluminium, because aluminium has only one redox state. The two mineral goethite and hematite, obviously they are the most common and abundant, existing in all soil types. And when you look at the soil map here, this region between these two dotted lines is dominated by what we call tropical, subtropical, highly weathered soil. So most of these soils, they probably will have iron oxide as the dominant fraction. They come in many different forms and colors, and as you can see from some of these examples of soil profiles, there is the dominance of these minerals is evident here from the dominant color, but more importantly, the chemical reactivity of these soils is governed by the properties of goethite and hematite, or combination of the two. And not only in highly weathered or tropical soil, these are important. In a lot of the relatively young soil, you see the presence of iron oxides in different ways. Redox conditions are very common in many European or North American soils. And in those soils or in those conditions, you can see the evidence here. Mottling is very common, and in those circumstances, the iron oxides, when they go through these redox reactions, they are affecting a lot of biogeochemical reactions in those systems. And then there are some systems where probably iron oxides dominate the whole system. Here we have few examples of acid sulfate and acid mine draining samples. So here you can see that this is somewhere in the southwest of England. This is in the central part of Australia. And in all these systems, iron oxides, they go through different changes of phases. Mineral starts from ferrihydrite, then they convert to more stable phases via some of the metastables such as sweetmanite or jarosite. And they can occur in association with highly saline or highly acidic conditions. Okay, so having seen that iron oxides are very common and they are dominant or could be dominant in lots of systems, how they control or affect the geochemistry or fertility of soils? There are probably three different ways of summarizing all those roles. The first one is through the adsorption reactions. Here you can see from these schematics that iron oxides can adsorb a lot of essential elements through either inner sphere complex formations predominantly or outer sphere complex formations. They could incorporate metals or elements in their structures. So there are a lot of elements which could replace iron 3 in the structure and become part of the iron oxide structure. And then these redox reactions, which can be deriving or affecting the availability of a lot of elements. arsenic is very common one. And there is a lot of work being done even in the last 5 to 10 years, where in a lot of delta regions in parts of Bangladesh, India, where people are demonstrating that how during monsoon and post-monsoon season these redox condition changes and affects the availability of arsenic. So all of these pathways, they can operate separately or simultaneously in certain systems in affecting the fertility and geochemistry of soils. Let's look at some of the examples. And before I do that, I just wanted to put this diagram where we looked at a lot of these trace elements and their association with iron oxides. These are the samples where we concentrated iron oxides, and then we dissolve the iron oxides in acids, and then see how these elements, they are dissolving in proportion to iron oxides or iron. And as you can see, in number of these elements, the relationship is pretty strong. It's not a straight line, but nevertheless, it's you can see in case of chromium, nickel, manganese, cobalt, to some extent aluminium and copper as well, that a lot of these elements are being released with iron. So what we proposed as a result of this one was that a lot of probably these elements, they are incorporated in the structure of iron oxide. Some of them probably are not. They are either existing as a separate phase. As you can see here, there is a lot of N in here as well. So that separate phase is dissolving and giving a completely different train. But nevertheless, it shows a fairly clear trend that a lot of these elements, they are either adsorbed very strongly and being released during acid dissolutions, or they are incorporated in the structure, so they are being dissolving along with iron. When you look at the list of elements which substitute for iron, you see the size is highly variable, almost varying by a factor of 2, starting with aluminium, which is about 0.05 nanometer, and going to lead, which is nearly 0.12 nanometer. So the highly different cationic sizes and different charge. They vary anything from +2 to +4 charge. So a lot of these elements which have very different size, different charge, they can substitute in the structure of iron oxides, and obviously it has consequences in terms of reactivity or the product which will be formed under those systems. Just briefly to remind you the structure of goethite, it's just a kind of parallel chain of double octahedra, and the point to note here is because of this relatively open structure, there is a lot of capacity for these different cations to get incorporated, because there is a lot of space for these octahedra to stretch, shrink, and distort for the foreign element to get incorporated in the structure. The first one obviously was demonstrated for aluminium, and almost 1/3 of the iron 3 can be substituted by aluminium, and that obviously has effect on the unit cell parameter of the mineral. Here you can see the cell parameter A and B almost linearly decreasing as a result of substitution. And as you can see, the size of aluminium is obviously much smaller compared to iron 3. The same trend was not evident for dimension C, where it's not following what we call the Vegard rule. Similarly, for cobalt, or rather I should say in case of cobalt, for the limited number of samples, you can see the all unit cell parameter, they decreases as a result of the substitution of smaller size cobalt for ferric iron. If you look at the copper, which has got slightly bigger size, and it's a divalent compared to ferric. In case of copper, this is the sample with the 4 mole % copper substitutions. So you can see that there is hardly any goethite when you have 4 mole % copper. Up to 3 mole%, there is some incorporation of copper. When you look at the unit cell parameter, we did the synchrotron X-ray diffraction of these samples. Although the size of copper is larger than ferric, the unit cell dimensions, they are not increasing as you would expect, or as you saw in case of cobalt, where all the dimensions were decreasing. Copper has what we call a Jahn-Teller effect, so the octahedra get distorted and the effect is different. Only the unit cell parameter A is increasing with the increasing size, whereas the dimension B and C, they decreases. So the octahedra get highly distorted as a result of the small amount of copper in the structure. That's quite evident in case of copper. When you look at the structure, this is pure goethite, and that's the 3 mole% substituted goethite, which you can see the particles become much thinner and smaller in size. We also looked at the substitution of cadmium, which is this time it's very large, 0.95 compared to 0.65. One thing that we were able to substitute a much larger amount of cadmium in the structure, up to nearly about 10 mole%, and all the 3 dimensions, they increased with the increasing substitution of cadmium. And this effect on crystal size was in some way similar to copper, that the crystal dimensions decreased. So crystal become much smaller, specific surface area become much larger, and you can start seeing the implication of these things is that, okay, the cadmium get incorporated in the structure, but if you will have goethite produced with the cadmium substitution, that will have much higher specific surface area and much higher reactivity compared to pure goethite. We have, since the single, we have tried with the double, triple, and tetra metal system substituting, because that's what happens in the natural conditions. When you are looking at the acid sulfate soil or acid mine drainage, there are a lot of these heavy metals or trace elements available in large quantity, and the probability of their incorporation in goethite structure is much larger. So for that reason, we looked at the incorporation. One thing which I want to point out from this slide is that in case of copper, you can see you get the formation of hematite preferred over goethite. Okay? Copper was not substituted too much in goethite structure. We have seen that before, but when you look at the multiple system, in copper case, you get preferred crystallization of hematite in the system. Different amount of metals were incorporated in the mixed system, and I'll present you a summary of those later on. I think there's too much information here. What the summary is that in single systems, the amount of metal substitution for chromium, zinc, and to some extent probably cadmium also, they were quite similar, much greater than lead. When you combine the 2 elements together, once again, zinc and cadmium, they were able to substitute, or the amount substituted for these 2 elements were much greater than lead. And in case of tri and tetra system, also the similar sort of these 3 elements which get incorporated easily in single system, they also got incorporated in the mixed system. Just a very quick demonstration of what happens to the actual structure of goethite with the substitution of these metals. If you look at the structure of goethite here, you can see that octahedra, or the distance between iron and oxygen or iron and hydroxyl, is different. You can see these, the iron oxygen distances are about 1.95 angstrom, and in case of iron hydroxides, the distances are about 2.09. The metal distances in case of the goethite structures, they are indicated here, the edge sharing and the corner sharing and the second edge sharing. So we got 3 next door neighbors at a distance of about 3.01, 3.23 and 3.45. When you look at the local structure for the metal substituted systems, you see that there are clear evidence of distortion of the octahedra or of the local structure. In case of chromium, which is where we are about to fit about 10 mole% of chromium in the structure, you can see that the metal oxygen distances were similar. You were not able to separate the oxygen and hydroxyl distances. In case of cadmium, which is much larger than ferric iron, you can see the distance between metal and oxygen hydroxyls have increased significantly. Also, one of the other metal-metal distances also increased. Likewise, in case of zinc, this distance has changed, and this distance has become, the metal-metal distance has become bigger. So what you are seeing there is that as a result of the incorporation of these things, you can see the evidence for the distortion or slight changes in the local environment or local structure around the metal. For lead, the situation was quite different. We were able to put only small amount of lead in the structure, and you can see that there are some rather large changes in the local structure in the goethite. And that's why you can see, because of these big changes in the structure, the crystals were not bigger, and the structure was not able to accommodate a large amount of these elements. Where the strains are smaller in the structure, those elements can fit in large proportion or large amounts. That's once again is demonstrated in the TEM micrograph of these samples. Once again, here is a pure goethite, and if you look at the copper and lead substituted goethite, you can see the crystals become much smaller, and sometime you start seeing these two different types of morphologies, some small sub-rounded, rounded crystal, as well as some acicular needle-shaped crystals. One more example I want to give. So we have seen that all these metals, they can get incorporated in the structure of goethite. But if you have those metals present in the system, they can also affect the formation of a particular species of iron oxide as well. And here in this, the conditions we have used for the synthesis of goethite here is fairly gentle, that we were maintaining the pHs around 7, so buffering with the sodium bicarbonate in the presence of copper and zinc. I don't want you to read any of these in detail, but after about 48 hours, this is the pure system. You got almost everything formed into goethite, started with a lot of siderite and other things, but we have got more or less pure goethite. Similarly, in case of, or in the presence of zinc, we are able to get goethite. However, when you look at the system with copper, you can see there is a fair amount of lepidocrosite in the system. So what we are seeing here is that when you have copper present in the system, goethite formation, once again, if you remember, we saw it earlier as well, that copper interferes with the crystallization of goethite, and here lepidocrosite is preferred in the presence of copper. If you look at the diffraction pattern of the final product in the presence of zinc, copper, and copper zinc together, zinc, pure goethite, copper, fair bit of lepidocrosite, and copper zinc, it's goethite. As we saw in case of the pure system of copper, the amount of copper, although we are saying here this is the nominal amount, 10 mole%, but this didn't go in the structure of the mineral. Only a small amount of copper went in the structure, and that's why these the width are not affected as much as they are in case of zinc. That was also clear when we dissolved those samples, that a lot of copper appeared well before iron, so it was predominantly adsorbed on the surface rather than in the structure. Whereas in case of zinc, as you can see, the dissolution is more or less fairly close to 1:1 line. And in the combined system also, it's a lot more closer to 1:1 line than the pure copper system. So what we are seeing here is that copper obviously is enhancing the oxidation of iron, and in that process it affects the formation of a different phase than goethite. When we look at the adsorption of these trace elements on iron oxides, I just want to make point that often when we synthesize goethite, we make much larger perfect crystals with very small surface area. Similarly, if you look at the same sort of material from soil, the crystal is nowhere well developed as in case of the pure system, and much smaller, probably a lot more defects in the structure, and also has got much larger specific surface area. And what it does is, when that sort of material is present in the soil system, the adsorption of a lot of these trace elements is going to be much higher than what you would expect from the pure species. So not only you have the incorporation of lots of metals in the structure of iron oxides, you will have adsorption or association of a lot of these trace elements with iron oxides as a result of their adsorption on the surfaces of these minerals. And one thing which is different here is remembering that copper and lead, they were not getting in the structure of goethite. When you look at the adsorption behavior, they are the one which are adsorbed most compared to the other element. So there are two clear separation here, that elements such as copper, lead, they are adsorbed on the surfaces, whereas elements such as zinc, cadmium, chromium, they are more incorporated in the structure of iron oxides. This work came in about 2004, and I think Bob was part of this work. This was done by CSIRO, and this has got a lot of implications for many of you if you are interested in geochemistry. When we are looking at soil contaminations, quite often we have to look at the background concentrations for a given soil type or given soil type on a parent material. Okay? Different parent material soils may have different background concentration. In this paper, what the authors did was they looked at the background concentration of a lot of these trace elements based on the iron concentration, because of the strong association of these trace elements with iron. Okay? And there are lots of these samples. There are samples from many different countries here. There are samples from Africa, Thailand, Australia, and there are some samples from parts of Europe as well. So these samples comes from all over the world. One thing which is reasonable, and there are two different soil types, by the way. There are general agricultural soil where the top soils have been sampled, and then there are soils from the remote areas which have not been applied with the nutrient elements or fertilizers. So these are the soils where you would expect the sort of natural concentration of these elements. So what you see here is that in this case we have got arsenic, copper, cobalt and nickel, that all these elements, they are broadly associated with iron concentration. So if you want to define the background concentration of these metals, probably you can use iron as a proxy. And it's also true for some of the others as well, chromium, lead and zinc. So there you can see a clear applications of those processes what we have discussed, where either these elements are structurally incorporated in the structure of goethite or hematite, or they are adsorbed on the surfaces. But as a net result of those two processes, these elements are strongly associated with iron, and therefore we can use iron concentrations to predict the background concentrations in this system very broadly. I think I will probably skip this summary. We already have gone through this. I'll just now move on to kaolinite briefly. Now in kaolinite, most of you are familiar with what, when we talk about kaolinite, you just look at these perfect hexagonal crystals of kaolinite. But if I tell you that the soil kaolinites are nowhere near to the kaolinite what you are familiar with. These are some of the examples or micrographs of soil kaolinites. Much smaller crystal, rounded, sub-rounded and defective crystals. And here is a comparison of a geological kaolinite with it. In case of kaolinite, there is a very little permanent charge in the structure. Most of the activity comes from these two functional groups on the edges of the particles, aluminol and selenol. Okay? Aluminol can protonate and deprotonate, whereas selenol only deprotonates. What happens as a result of that? So we have different pK value for these functional groups. These aluminium functional groups, they dissociate at much lower pHs compared to the silicon groups. What we have found in case of soil kaolinite is that all soil kaolinites we have looked at from at least half a dozen countries, they have at least 50 millimoles per kilogram cation exchange capacity, which is much bigger than what you would expect based on even the poorly crystalline phase or pure geological based kaolinite. So there is some sort of structural defect, and this has been done here. Jock Churchman has produced this relationship between surface area and exchange capacity. That's where you can see most of the kaolinites have got cation exchange capacity between 5 to 10 centimoles per kilogram compared to the geological sample. So they are much more reactive. Why they are reactive? Probably combination of much smaller size, and those surface functional groups contribute lot more exchange capacity. Also there is substitution of iron in the structure, and I will probably skip this one. There is iron in the structure of these kaolinite, as shown here from the single crystal microscopy, that a lot of these soil kaolinites, they have up to 2.5 mole% of iron in the structure. And that iron, mostly it is, we have seen it's an iron 3 form in the octahedral sheet, but small amount of that iron could also be either in the tetrahedral sheet or could be in slightly, not slightly, but in reduced form, iron 2 form, that might contribute a tiny amount of permanent charge in the structure. We did look at the exchange capacity of lot of kaolinite, and just to give you some flavor, you can see exchange capacity of soil kaolinite here compared with the clay fraction of the Georgia kaolinite, 10 times more higher cation exchange capacity, nearly double the specific surface area. And this one is more important, phosphorus adsorption capacity. These kaolinites have capacity to adsorb phosphorus on the surfaces. So that has implications in these tropical highly weathered soil where phosphorus is probably the most limiting crop nutrient. I'll give you a couple of or one example of the smectite. Smectite is a common mineral in vertisols, and you can see that we have got quite a large portion of vertisols in the world, and in Australia probably we have the largest occurrence of vertisols, quite a large part in the sort of northeastern part in 2 states, Queensland and New South Wales. And here you can see some distribution of vertisols in the US. These are very productive soils, and they have distinctive properties. They've got very high exchange capacity, and they are considered to be the most productive soil in many parts of the world. The example I want to, or the point I want to make in case of smectite, in case of vertisol, is that a lot of these vertisols have the smectite dominated clay mineralogy. And the smectite is different than the smectite what we are often used to, the Montmorillonite type of smectite. Here we measured the charge of these smectite in soil, and if you look at this right panel here, this is one of the soil smectite, N13, and here in red is your Wyoming bentonite. The charge in Wyoming bentonite is about 0.26, whereas the smectite in soil has got a charge of nearly 0.6. So much higher, much greater charge in smectite. Also, the smectite in soil contains a lot more iron and a lot less magnesium. And similar sort of smectite have been reported elsewhere as well, in Texas, or I should say in the regions where there is large occurrence of these vertisols. Okay? Morocco and Texas or the US are two good examples for that. So what are the implications of this iron, this smectite? Well, a number of those are probably clear from these three examples I have given here. Stuckey long time ago showed that the structural reduction of iron in the octahedral sheet obviously increases the cation exchange capacity of these soils. And also it leads to the fixation of trace element as well as potassium. Remember, this potassium is very, very important. It's one of the major plant nutrients in soil, and when I'm talking about vertisol, these are very productive soil. If these soils get under redox conditions, then they will have implications on the availability of potassium, likewise ammonium. This is probably my last slide. So far I have demonstrated that minerals such as iron oxides, kaolinite and smectite can have effect on the availability of a lot of major nutrients or trace elements, heavy metal. This is a recent example of a study done in Germany, where they have looked at the interaction of organic matter with clay minerals. And they put a labeled carbon in soil. This is the natural soil. These are the mineral and organic associations. And when they put the new carbon in the soil, where they identified this new carbon was associated with the defective part of the mineral surfaces, where the mineral surfaces are rougher. Okay? So if your particles are much more cleaner, smoother, the organic matter is not interacting. But where the minerals have rough edges or defective structures, probably there is a lot more probability or chances of organic matter interacting with mineral. So with this, I think I will finish with this slide, or I hope I have demonstrated enough that imperfect mineral controls soil fertility and geochemistry. Thank you for your kind attention.